Okay. Hello, everyone. Today, we're going to finish assignment 2, hopefully. Is anybody done? Exec fork. OK. So let's review. Last time, we've mentioned that we have 3 abstractions for the file syscalls. We said that we have file descriptor, that is an index into the file table and points to the file handle. And we have also a file handle that points to a file object. We also have a file object that is the physical file on disk. So why do we have 3 levels of indirection? Because we need to enforce 3 different or separate sharing policies. So the file table is private to each process. The file handle is also private to each process as long as you don't fork. Once you fork, it will be shared between the parent and the child. The file object is shared system-wide. And this is basically what we call as the vnode, which is a framework already implemented for you. So in OS 161, we said that the file descriptor is an integer indexed to the file table. File handle is a structure that is process-wide. And file object is a system-wide. It's a vnode, which is a shared system-wide. So this is how the process model should look like. So we have a parent process. We have a child process. As we can see that the file table is private to each process. And the file handle is going to be shared between the parent and the child of the parent fork. And the file object is basically shared system-wide. And we had some question regarding the file object, since I've said that if you have 2 processes that open the same file through different file handles, then does the vnode handles the synchronization between them? The answer is yes, you don't need to handle this. This is already handled for you. So yeah, the file handle is shared between the processes that forks, and the file object is shared system-wide. As we can see that the console files that we discussed, that we have stdin, stdout, and standard error. So these are special files in the sense that there is no offset concept with the console files. So you only append, when you write, you only append to the end of the file. And when you read the user input. So you're not going to ask for 100 bytes of the user input to be read. And what makes them special is that they have a fixed file descriptor. So 0 should point to stdin, 1 should point to stdout, and 2 should point to standard error. We've also mentioned when should we initialize it. So it should not be initialized whenever you create a process. It should only be initialized when you create the first user process or user thread. And then your fork should handle copying these indices as you fork. So whenever you fork, you should only copy the reference to the stdin, stdout, and standard error. Yeah, that's pretty much it. And also, this is the vnode that we said is the physical file on disk. The vnode functionality or a framework is already implemented for you to use. And you have a useful operation, vread, write, syscall, that you can use with your file syscalls. There is also a virtual file system which is built on top of the vnode. And it has a very useful functions like open, close, change directory, and get current working directory. So we've also said, since you have all these functionalities implemented for you, what you need to do is design the file table. So if you ask me, what should I do as the first step? OK, go into the process structure, which is defined in proc.h. Define the file table. And from there, you can start your assignment, basically. Because once you define the file table, then you know that the file descriptor is an index into the file table. The file table should have a reference or a pointer to file handles. So from there, you can start working or solving the assignment. So what you need to do for the file syscalls part is design a file table, design a file handle, and check if the argument passing, check if the arguments are valid or not. So this is basically what you need to do for the file syscall. Other than that, you only, once you're done with designing the file table, file handle, and argument passing for each syscall, you basically go and call the vnode operations or the VFS operations that are given to you. This works with most of the file syscalls, except for read and write, where you need to initialize. Also, I think get current working directory requires you to initialize a UIO, which we explained in the last recitation. And we've said that this is basically a structure that takes where you should save the content that are read or written, the offset, and other information. So other than read and write, the rest just like going to be designing, having a file table design and the file handle design, and then you need to do the argument checking. Any question on the file syscalls before we move on? Yes?
What do you have to do for the argument checking?
Sorry?
How do you actually do the argument checking?
That's what we explained through the copy in, copy out functionality. So you have these functions that if you just check the previous recitation slides, you have the path to them. So it's just like a functionality. You have the copy in, copy out, copy in string, copy out string. These 4 functions you use just like to detect any kind of violations. These pointers, you use them with the pointers, because when you pass the pointers, you only get the address. You're not getting the value which is in the user space. So you need to check what values are these pointers. First, you check if the pointer is valid, and then you check if these values are valid or not. Any other questions? OK. So today, we're going to hopefully finish the assignment 2. We're going to go through the process structure in OS 161, and then we're going to start going through the process syscalls for exec v, wait PID, and exec and get PID. The deadline is going to be 3 days on Friday, 5 p.m. OK, so process structure. Process structure basically is similar to the file table structure. So you need to have a data structure that keeps track of the processes that you already have. And it should have several information. So what is already or currently defined for you is defined in current include proc.h. So if we check that file, we see that the process structure here have a name, spin lock, and number of threads. You don't need that because, as we said, for OS 161, each process only have 1 thread. So you don't need to worry about multi-threading. Address space and current working directory, a pointer to the current working directory. So this is what you have. What else you need to add? So if you think of the process, you need to have a reference to threads. So each process could have, as we see in that figure, that every process could have several threads. Or as we say, that in OS 161, every process have only 1 thread. That's what we assume. So basically, we should have some kind of functionality that the process can identify what thread it has, and the thread, it can identify to which process it belongs. So this is one of the things that we need to maintain in a process structure. We also need process address space, which is already there for you. Current working directory of the process, which is already there for you. You need to define, as I said, a file table for the process to maintain the references to file handles. And also, you need to define a PID, which is a process ID. Each process should have a unique identification number. So this is what we call the PID. And also, each process should have a PPID, which is the parent PID. It should maintain who is my parent. We have also 2 other variables that we need to maintain, which is exit status. We need, through that variable, we can, for example, ask if that process has exited or not. And you also need to keep the exit code. If the process exited, then the exit syscalls should return an exit code which should be saved in a variable in your process structure. You should also implement a synchronization. Why? Because if I am the parent process and I fork, I create a child process, then I should be blocked up until that child process exits. So this is why you need to decide which synchronization primitives that you already implemented in assignment 1 you should be used. So you can use it with the wait PID for the parent process to be blocked or to go to sleep up until the child process signals exit and signals the parent process. So this is basically how, or in general, how should that process structure look like. That doesn't mean this is everything. No, that's not everything. But this is the major parts that you need in a process structure. Any questions? OK. Now, since we defined the process structure, as we said, we need to have a process table. So a process table, as we said, is something similar to the process or the file table. And we will use the PID to map between process structure and a process. So given a process PID, we should be able to retrieve the process structure. And also, a process and this thread should be able to identify each other. As we said, keep in mind that in OS 161, every process has only one thread. And each one of them should be able to identify the other. So process table design. What are the requirements for process table design? Almost similar to the file table design. So when I fork, I need to be able to allocate a new index in the file table. And after I allocate a new index in the file table and I create a process, I should be able to allocate a PID, a process ID. Now, there are different people, so there are different strategies how you should go about allocating or getting a new PID. Some people will only use the process table index as the PID. And some other will only use just like an increasing counter to allocate the PID. So since the PID is unique, the best practice tells you it's better to use an increasing counter for allocating a new PID. And yes?
Is it very important to reuse the PID once it's exited?
Well, as I said, so you mean to reuse the PID? So it's not. So as a best practice, that's why we said since it's a unique number, then it should be just like increasing counter. And you just like, for every process, you need to create a new PID, even though if we have other processes that already exited and they are done with the PID. So some people just use as the file table, they use the index in the process table. And some other people use an increasing counter to allocate new PIDs. And as I said, so the best practice is just like using an increasing counter. And you can see that in limits.h, you already have a max for the PID. So PID max. So this is already defined for you. So once you reach the max, you need to just like use the modulo and go back again, and instead of using the index into the process structure. So as I said, when we fork, when we create a new process, we should be able to identify a new available index. You should be to allocate a new PID, whether using the table index or just like allocating through an increasing counter. And given a PID, if I give you a PID, your data structure, your process table should be able to retrieve the process structure for that PID. Also, and now when I'm done, I want to exit, then you should be able to recycle the table index. Let's say you're using an increasing counter for the PID, then the index in the table can be reused. There's no problem with that. And also you should be able to deallocate the assigned PID. So if you used the table index as the PID, then as you recycle that table index, you can then reuse the PID again. If you're not using the table index as the PID, then you just need to be able to deallocate that PID. So whenever, for example, I ask or request the process structure for that PID, it should return me that the PID is invalid. And this is what you need to handle when a process exits, or called the syscall exit. Any questions on the process table? Yes.
Can we edit limits.h like the maximum PID?
It's better to leave it as it is, and just like use the module and to go back again if you reach the maximum number of processes, let's say. You also have other, so for example, this is the maximum number that you can open files. So this is the maximum number of files that can be opened at the same time. So you have other also maximums that are already defined for you, and you can use either with process syscalls or file syscalls. Also note here, you can figure this out, that the PID min is 2. So that means you should start from 2, not from 1 or 0. Yes?
But you have to assign 1 to the kernel, right? Explicitly.
I don't think so. I think you should only care about the user processes. So.
When the first process is initialized, that cannot be true.
Okay, I need to look into that. But what I know is you need to start from 2 for the PID. So if you roll back from, or if you want to start using, or if you want to allocate PID using the increasing counter, you should start from the PID min, which is 2. I know the reason, but I can't recall it now. I saw it, so. Let's continue now. Okay, so any other questions for the file table design? Okay, so syscall fork. So this is just like a user program that we should be familiar with for fork. Basically, you call fork, you create a new process, and then if the PID is -1 or less than 0, then that means the fork didn't go through. If it's 0, then that means the current thread is I'm the child. And if it's other than or greater than 0, then that means I'm the parent. And as you can see, so if it's the child, then it will just like, there's a hello world, it will just like print, and then exit, and returns the exit success. And the parent, for the parent, once it forks, it will go into, it will call the wait PID, and wait PID, since the child didn't exit it, then the parent has to go into sleep, or has to wait, to be blocked up until the child exit. So this is how the fork syscall should look like from the user program. So what does fork do? As we said, fork create an exact copy of the current process with exceptions. There are some few exceptions that it's not an exact copy, so almost an exact copy. After fork, so the process that called fork is the parent process, and the process that it created after fork is the child process. So what to copy to the child process? So this is one of the questions that you need to consider, which is, what should I copy into that child process, and what shouldn't I copy into the child process? What you should copy is the parent's trapper frame. So here I need to explain one thing. So if you recall, when we discussed how to add a syscalls, I've mentioned that you need to go into the manual. The manual tells you the syscalls and what arguments receive, what argument it returns. So these arguments in the manual, you should have them in your syscall.c when you add another branch into the switch statement. But that doesn't mean you cannot add more arguments into the syscall. And this one of the stuff that you need to figure out what other arguments your syscall needs. So for example, fork does need the trapper frame, and we said that the trapper frame is basically a structure of all the CPU's registers. So in trapper frame is where we save the context of the user process before it gets trapped into the kernel. So you need to copy the trapper frame, which is the context. You need to also copy the address space of the parent. You need to copy the parent's file table. And what you shouldn't copy is the parent ID. So the new child process should have its own unique ID. So you need to allocate a PID for the child process, and the PPID of the parent shouldn't be copied into the shouldn't be copied over to the child because it's pointing to the parent's parent. So you need to set the PID of the child to the parent who called fork. And also the return value of fork. So if I'm children, I need to return 0, while if I'm the parent, I should get the PID of the child. So these are the things that you need to copy, and the stuff that you shouldn't copy. So how to copy? So as we said, we need to copy the trap frame, we need to copy the address space, we need to copy the files table. So how to copy the trap frame? As we said, the trap frame is basically a structure. So you need to copy the trap frame into the kernel heap, which means you need to allocate a structure of type trap frame through kmalloc, and then by assignment, just like make the new value or variable that you defined through kmalloc of type trap frame, you need to just like make it equal to the trap frame that you received from the parent. So, and C should handle copying all the registers for you in that structure. So you need to copy the parent trap frame through assignment. How should we copy the parent's address space? So the address space in OS 161, you have just like, again, you have a framework that is there for you to use, and you might need to modify when you solve the assignment 3. So if you go into kernel include address space.h, you will see here that we have a set of functions that are defined for you and you can use. So these functions are currently, as we can see the note here, tells you note that when using dumpvm, address space.c is not used, and these functions are found in dumpvm.c. And once we start solving assignment 3, you need then to start thinking about implementing these functions here. So these are the functions that are available for you to use with the address space, manipulating the address space. So for example, you have as create, as copy. So as copy is the one that you're going to use for copying the parent's address space into the child address space. You have also as destroy. So you have a bunch of functions that you can use to handle the address space for assignment 2. So this is for the address space. As we said, we're going to use as copy to copy them. And we also have the parent's file table, and this is you implemented. So you should know how you should copy your file table data structure. So now, what about the other stuff that we shouldn't copy? So the PID, as we said, since it is unique to every process, then it should be allocated, or you need to allocate a new one. So a new one in a sense that if you're using an increasing counter, or the one that is you have an invalid index in the process table that you just allocated for your new process, you can use that index. The PPID then should be set to the parent's PID, and then you have the return value that you need to figure out how you should handle it for the new process. which is basically using the MIPS return value convention that we mentioned in the previous recitations. Like you need to pass the return value in V0 if the value is 32-bit, or V0, V1 if 64, and A3 register is used to just like set to 0 if you succeed, if the syscall succeed. So as a result, to summarize, so what should fork do? So you need to allocate a new child process with a new PID. You need to set the PPID to the parent PID. You need to copy the trap frame. You need to copy the address space. You need to copy the parent's file table. So the trap frame, address space, file table are all copied from the parent process. And then once you're done with copying, then you need to call the thread fork to do the remaining work. So the thread fork will basically handle the whatever remaining work that needs to be done. And then, so if you are in the child process, then you should return 0. If you are in the parent process, then you should return the child PID, the process ID. So that's all for fork. Any questions on fork? Okay. Exec fee. This is the most difficult part in your assignment 2. So exec fee and run program. So let's first compare these two. Run program you already have. So what is run program? Run program currently implemented for you, and it is responsible to run program from the kernel menu. Exec fee basically takes the newly created child and replaces the current running program with the program that is loaded for that new child. So if we recall in the previous recitation, I gave an example for dump2 where you use the shell to call echo. So let's say I use the shell to call foo program, or I want to run the foo program. So the shell is a process or a thread. If I call foo program and I want to run the foo program, so what will happen is I'm going to create the shell process, going to create a new, going to fork and create a new process for the foo program to run. So the shell process is the parent process. The foo process or thread is the child process or thread. So once the child executes, then the shell process basically will block, and it will wait for the foo program to finish execution. Once it's done execution, so then it will return the exit code. And at that point, the parent process will be signaled, and it will, just like we will return to the shell. So if we don't do this, basically what will happen, if we just call exec fee in the parent process without forking, that means I'm going to replace myself, the shell going to replace itself with that program. And you won't have any more shell. So to keep the shell running, you need to fork a new thread, run that program in that thread while the shell is blocked and waiting for that thread to exit. Once the program finishes executing, then it will exit and return the control to the shell thread. So this is basically how the exec fee works. So basically, it will take the new created child process, replace its currently executing program, which is, in the shell example, the child thread running the shell. So it will be replaced with the foo program, and then start executing that newly loaded program. So exec fee and run program are similar in some ways. So run program uses VFS open as a create loadel as define stack that will return you a user stack, and then at the end it will enter a new process. So that part of the run program should be identical or similar, let's say, not identical, similar to the exec fee. What additional stuff that you need to do in exec fee is, or let's say the differences between them. So run program doesn't take argument vector. So with exec fee, if you see the signature of exec fee, you'll see that you're getting an argv pointer to array. So this is the argument vector. So that's what you're receiving with execv, but you're not receiving with run program. Run program needs to initialize the console files. You don't need to initialize console files with execv. Execv should handle argument passing since it is receiving that argv pointer. So argument passing from the user space to kernel space and back to the user space. But run program shouldn't handle this because it's not receiving any arguments. So these are the differences. So we can define execv as a run program plus argument passing. Any question up to this point? I hope it's clear now. You have a better understanding of how exec works. So now let's go through an example. So let's say in OS 161 you call arg test and you pass these three arguments, foo, OS 161, and bar. So let's ignore the program pointer and let's just focus on the args pointer. So this is what the program receives, or when you call the arg test, it will basically receive an array of pointers pointing to the arguments. So as you can see, args, the arg0 should be points to the program path or program name, and arg1, the index 1, should be pointing to another or pointing to the string foo, and arg2 should point to the OS 161, and arg3 should point to the bar. And then it should be null terminated. So this is the first part that you will get, and then this before you execute execv. When you execute execv, the signature tells you that it should receive the program name, which is args, the 0 index in the args array. And also it should receive a pointer to the, or the args pointer, which is pointer to array of pointers that pointing to the arguments. So this is the whole picture that once we call the exec should be. So the program is pointing to the program name. And as you can see, the first index or the 0 index in the arguments array is also pointing to the same program name, and the rest pointing to the arguments that you receive. So this when I call the execv. Now, how does execv work? So as we said, it's just like the same as run program plus argument passing. So the first step to do, since you're receiving arguments, then you need to copy arguments from the user space to kernel space. And then you need to do whatever run a program does, like the functions that we've mentioned here, just like VFS open, and you load the executable into memory, and then get a user-defined process, and at the end you will call the run enter new process. But let's ignore the enter new process. So the first step will be copying the argument into kernel space, then load the executable into memory, and the third step is copy arguments back from kernel space to the user space. Why? Because if we pass a kernel buffer pointer to the user has no access to the kernel address space. So you must copy back the arguments into the user space. Where should we copy the arguments? So we should copy it on the user stack. So here is the most difficult part of execv that you need to figure out. So we're going to copy the arguments back to the user. And how should we do it? Basically, so as we can see, this is the user stack. The user stack in the address space, if we recall the figure, the process figure, the user stack starts from the address 80 million. So that means from the top of the address space and growing downward. So this is the start point of a user stack, and that means as we add stuff to the stack, it should grow downward, and that makes us just like it's more safe and secure this way, to make sure that we're not going to access the kernel space. or the kernel space that we are not allowed to access. So how should we place the arguments? So this is one of the stuff that you need to figure out on how you should organize the arguments from the kernel space, how you should organize it in into the user space. How should you organize it? So this is one way of doing it. It's just like you need to, for example, first of all, you need to know that in MIPS, pointer should be aligned by 4. That means each, for example, each argument, or when you move the stack pointer, you should just like, or let's say the pointer, let me put it in a correct way. So the pointer should be of size 4 bytes. And this is how you should move. So first of all, since we have a pointer to array of pointers to the arguments, then we should, for example, place the arg0 into the, or let's say we can start this way, where we place the program name and then the foo. These are the arguments. And then since the array or the argv is pointing to the pointer of arrays, so each index in that array is of size 4 bytes. And we know that an array, the value of the array is basically an address. And the address of an array is basically 32-bit or 4 bytes long. So each index, for example, each index in that argv array is a pointer address. So it's a pointer to the string. So that pointer is of size 4 bytes. After that, then, so we should also place, other than the array itself that we should place on the stack, we should also place the arguments, or the arguments. So for the arguments is where you need to be careful. Why? Because now here you should keep the pointer aligned, which means that, for example, how should we store bar? So the bar should be just like, we know that every character is of size 1 byte. So we need to keep it 4 bytes. So that means I should store B in one, B, A, R, and then I should pad the fourth, let's say the fourth position, so I can align, just like move each index into that stack pointer by 4. So that's what you need to keep in mind. So for example, if you have more than 4, then OS 161 then should be just like OS 16 and then 1, and then you should have 3 padding, just like 3 null. Yes?
So how do we make sure that it's 4 bytes? Like, should we just divide the address by 4 and see the remainder with the alternate?
So let me explain this, and I think you'll get your answer. So just to put it in a simple way, you have a stack. How should you place this stuff? It's just like, first, for example, let's say I have foo as my first argument. Let's say it's not the path name. So how should I push the foo into the stack? It should be just like push null first, and then you push OOF. And then you go into the OS 161. So that means, as I said, you need to push 3 paths or 3 nulls into that stack, and then you push 1. And that means now we have aligned by 4, and then we have the remaining, which is OS 16 is already 4. So it should be like this. Yes?
If your argument is of length 4, should you provide 4 extra padding?
So the character, each character is 1 byte.
Yeah.
So as we said, for the each index in the argv array, so we know that a pointer is a 32-bit, which is 4 bytes already.
Yeah.
So you just, once you store that value, it's already 4 bytes. So yeah. But for the rest, where you need to just like push characters, you know the character is of size 1 byte. So you need to make sure that your stack pointer is aligned. So just like you move 4 by 4. Yeah. Brijesh, did I answer your question?
Yeah.
So yeah, this is how it should be. Yeah. So this is one arrangement. That doesn't mean you need to do it this way. No, you can just like do it in any way. What's important is that the argv pointer and the stack pointer. So when you return these pointers, you need to make sure that the stack pointers point at the just like below the arg0, and argv should also point to that place. So what's important for us is these 4 indices, or this the array, the args array. The other stuff that they are pointing to, it's not important to us. Why? Because where should we place them? Because we already have the address of these. So once we inquire the address from the array, we should get the value from that address. So this is one way to organize your stack pointer, and or when you return your arguments from the kernel space into the user space. So one of the also you can, for example, one of these things you need to do, for example, figure out how much space you need to allocate on the user space. So how should I do this? Using this. So for example, I know that I have array of pointers, 4 indices I have, then each index is just like 4 byte, and each one is pointing to these arguments. I can calculate how these arguments are, what's the size of these arguments by just like, since we have every character is just like 1 byte. From this, you can figure out what should be the offset, or how you should move your stack pointer. And so from this, you can figure out the size, the actual size that you need. You allocate that size, and you start pushing into the stack. I know it's confusing, but once you go through it, it should be just like clear to you. So the only important part is just like you need to keep it aligned, or 4 bytes of size 4 bytes. Any question on exec v? Yes.
So kind of what you asked, does it really matter if you really like pad, or does it just matter that you align?
So if you want to pad, so you need to pad, because how should you just like know at which address they are? So these are the way the padding will just like makes it easier for you to figure out at which address each argument is. And where it should end. So
Yeah. I mean, like, you want to keep them aligned, but it doesn't matter that you like put, you have to like 0 the data out.
Sorry, I didn't get your question. So
Is it important to fill in the spots that you're not using?
with no?
No.
Yeah, you should. Yeah, it is important to fill it with no. Yeah. Otherwise, if there is any other value, you should just like be confused whether this part of the argument or not. So yeah. Yes.
I'm sorry, I missed what you said about if it's more than 4 bytes. So if it's more than 4 bytes, we should be passing a pointer to it.
No. So for example, OS161, since each character is 1 byte, then we have 5 characters, so that means more than 4 bytes. So you need just like to push OS16, this is a 4 byte, and then you need to push the one with the 3 nulls, then that means the other 4 byte.
Okay.
Yeah. Any other questions? Okay. So the wait PID. So wait PID should be implemented along with exec, because these are related syscalls. So the wait PID basically is for the parent to wait for the child to exit. What you need to check is, again, argument passing. You need to check if the PID is valid. If the PID is valid, you need to also check if that PID belongs to one of your children. So if the PID doesn't belong to your children, then you're not allowed to wait for that PID. Sorry. You also need to check if the status pointer is valid. So If we go through the wait PID, you can see that we receive PID and we receive a status pointer, and then we receive options. So you need to check the PID is valid, and if you are allowed to wait for that PID or not. You need to check if that pointer is valid. You need to check if the options passed are valid or not. And also, you need to return an encoded exit status through the status pointer. So this is what you will get from the exit syscalls. And the exit syscall basically calls the current process to exit. So it will just like I am as a process, I will pass the exit code to the exit syscall, and I'll call exit syscall. The exit syscall basically will store the exit code in the process structure, and be aware that you need to use that macro to store the syscall with the user supplied exit code. You need to use this macro with the exit code. Why? Because you might have some other status that should be appended to that exit code, and this macro will handle this. It will take the exit code, append it, and return the exit status to you. And then you also need, if we remember in the process structure, we had two variables. One indicates if we've exited or not, and one gets the exit code. So you need to save the exit code in the exit code variable. You also need to save the exit status in the status exit status variable in the process structure. Once you're done with this, you basically call thread exit, and it should handle the rest. Get PID, this is the last syscall. Get PID basically returns the process ID, process PID to that calling process. So that's pretty much it for today. Any questions? Yes?
So going way back, back to limits.h, you said not to edit the basically the maximum number of PID.
Yes.
We ran into basically it was running out of memory.
Okay.
Because our process table was too large.
So you used just like the maximum number of process to allocate the. Okay. So basically we should have two tables. Just like if you use array, just like array for file table and array for process structure, then you shouldn't run out of memory, because many people do it this way. I mean, using arrays. But if you're running out of memory, it's either you're leaking memory, or there should be something in the code. Or also, I can just like make double check if it is possible to change the values in the limits, but I believe there is a reason why these limits header file is there. So that's I need to double check.
Like to edit it as like for the implementation. So.
You can edit it and check if see if your program goes through or not. I mean, if it run correctly or not. But for testing, I don't know whether you need to keep it the same or not. I should double check this if it's fine or not. Yeah.
So like when you run fork bomb test,
Okay.
it should run out of memory, right?
Yeah. So I think the fork bump just like tell you once it tells you
It said it's
run.
loop.
Yeah. Just like
Yeah.
run out of memory, you should be fine. That means success. Yeah. Any other questions? I hope it's clear to you. Good luck with assignment 2, and thanks for coming. See you. Oh, have a nice spring break after this. Yeah.
Question. I've been trying
Oh,
to submit.
just a minute. Let me just.
Yeah, sure.
Sorry.